So here's a little outline for today. I'll start with some pleasantries. I want to give you a little bit about a non-local analysis overview, because I know this isn't a conference on non-local analysis, but I think there's a lot of overlaps with what I've been seeing about graphs, about propagation of information, long-range interactions. Those are things I'm interested in. The applications that I've been interested in recently, I think will demonstrate some of the analogies that I hope to capture. The ones I'll talk about are in electrochemistry and corrosion, but how you build the models, I think, are applicable in the settings that we've been sharing here at this workshop, and that's what the New Horizons section is about. I really want to thank the organizers. This has been a really great concept workshop, and the National Science Foundation. If anybody has an opportunity to check out Cracking the Secrets of Math, my undergraduate students actually started this podcast that brings together interdisciplinary areas of mathematics anyways, like computer science, physics, mathematics, chemistry, biology. And so I've really enjoyed hearing other ways mathematics intersects with cognition and neuroscience and stuff like that. So, and to NASA, thank you. A little bit about, I wanted to say a little bit about Cal State Channel Islands, but before I do that, I wanted to also let the audience know that actually we will soon be announcing a potential data associated assistant professorship in our mathematics and statistics department at California State University Channel Islands. California State University Channel Islands, I will warn you, is a terminal master's degree granting program in Ventura County, California, about 6 miles from the beach. I'm just putting that out there. We have a research station in one of the Channel Islands. The most famous of the Channel Islands is Catalina Island. I'm sure you guys have heard of that one. We have a research station in Santa Rosa Island, and that's why we're known as California State University Channel Islands. I'm also happy to share why we're not known as Camarillo State. Camarillo is the city that we're positioned in. We're a Hispanic serving institution. That means it's an institution that was created to serve the community, but maybe not so intentionally created to serve the local community. It's a very vibrant community, a lot of historically marginalized populations, but that's coming from a place with a lot of vibrancy and a lot to offer in terms of next generation solutions. So it's something that is offered a lot of opportunities. On the right is actually my research group, the group that I work with and occasionally get opportunities to publish with. On the left is the type of outreach type of things that I make my researchers do. We wrote a grant. The NASA portion is the grant. They give us augmented reality like workshop. It's like a mobile, they pay for it. It's a mobile cart filled with augmented reality lenses. And so we take it out, the kids come, they play with it, and we tell them, look, this is the future. And they're like, oh my God, you could be scientists. They're like, yes, this is the future. Nobody's investing in augmented reality vision anymore right now, but it's still, I wonder why. It's actually really fun. I also wanted to really throw out, I think you can barely see it. This is the sunrise tour in Tikal National Park in Guatemala. This is 2021 while I was on sabbatical. I didn't mention this. I'm an associate professor at California State University Channel Islands, and during the tutorials week, I submitted my portfolio for full professor. So maybe I'll be a full professor. We'll see. But during my sabbatical, I came here, and you can't. This picture doesn't do it justice how high up I am on one of these towers, but. I'm also really interested in projects like I think Ida mentioned something like these like geometric formations that weren't like studied mathematically. Well, maybe and the way the stories were told, that sort of interdisciplinary mathematics are also really captivating to me. So I came here because of that kind of reason, right? In the for these cultures, there was a lot of intersections between spirituality, political science, astronomy, and mathematics and architecture. And so those kinds of projects that bring together those concepts in ways that our current educational system doesn't explore them from a young age, I think offer insights to children. I know this is a really long introduction, but usually people trickle in. So I wanted to bring us back to this Scotty pinwheel thing, because as soon as I saw this, right, this was the cutest thing, right? I was sitting there, I was like, oh my God, it's so cute. And it almost brought me to cute aggression. Are you familiar with the phenomenon of cute aggression? So, but as I was sitting there and I thought, this definitely almost invoked the cute aggression in me. But this conference has also invoked something in a lot of us I think is relatable. For mathematicians, I don't know how many of you identify as a mathematician. I do. There's something we have, maybe I haven't given, maybe you have a word for it. I call it like curiosity intensity, right? And I hope that this is at least during my talk, I think in the mathematics community, there's a certain tolerance for curiosity intensity that in other disciplines we may not share the same level of curiosity intensity. In mathematics, maybe there's a higher tolerance for it. It's a privilege that in some cultures or in other disciplines they may not share. So something to be sensitive about. So sometimes I might come off as very curious and intense, and I mean it as a compliment. So when you do it to me, I receive it as a compliment. Just putting that out there. Now, I'm leaving you with this cute thing because I'm also going to tell you, these are AI generated. This one was a mega cute one of the previous one. There's a reason why there's a dolphin and a rainbow. I wanted to tell you a little bit more about my institution and why there's dolphins here. The dolphins will come back later, and just to keep you engaged with the dolphin, like when's the dolphin going to come back in the talk? In this portion of the talk, this is about the University, California State University Channel Islands. It's on our local tribe's land is the Chumash tribe. And the reason why our mascot is the dolphin, it has to do with this tribal culture. We have this origins story that the local population came from the Channel Islands. And they were island population, and they wanted to come to the mainland. And they asked a goddess to please bring them to the mainland. And the goddess said, I'll bring you to the mainland. I will build a rainbow bridge for you to come to the mainland, but you have to trust me and don't look down, or you'll fall through the rainbow and you will die. And so the native people, crossed the rainbow bridge to the mainland. But some people, of course, were curious and fell into the waters. And when the masses that arrived to the mainland realized that they lost some brothers and sisters, they asked the goddess again, our curious brothers and sisters, can you bring them back, please? And she said, I will not bring them back because they didn't trust me, but I'll convert them into the dolphins, and they'll keep you safe. They'll always be in the waters. And if it's true, if you go out, it'll never let you down. I went to UC Santa Barbara. It'll never let you down. You're having a bad day, you need to go out there. You'll look for your brothers and sisters. You'll find a dolphin out there. And so dolphins are going to come back, and this is the reason why. I didn't, otherwise, I tell people what I do to dolphins, and they're like, why do you do that to dolphins? It'll make sense later. So a little bit about my background. This is a haiku that I wrote to my original PhD love for mathematics. It's about dispersive differential equations. It's called dispersive DEs. Different frequencies, different propagation speeds, dispersive DEs. That says it all. If you know about dispersive differential equations, it's the idea that these are certain systems that when you observe their physical phenomenon, you can track solutions to these systems according to the speeds of propagation of individual frequencies. So the individual speed of propagation of the individual frequency will depend on that frequency explicitly. So I think wave equation is not so explicit. It's just plus minus one speed. That's not enough to be a dispersive differential equation. And so my haiku. And these were my collaborative friends. And actually I got this email to donate money to the AMS, and my picture was on there, and I was like, okay, I guess the AMS thought me and my collaborator Derek look like we convince people to donate money, and Sung Lee Oh. But why damage and degradation? So I studied control and stability of dispersive equation, but specifically the linear dispersion generalized Benjamin-Ono equation. It's a system of equations that takes you, it's a spectrum of equations between the KdV equation and the Benjamin-Ono equation. They're a little bit more known. The Benjamin-Ono equation has this singular integral operator term called the Hilbert transform term as its dispersive term. It's a really, really cool equation. And I studied that, and it was really cool. Singular integral operators I thought were really cool. And I met some mathematicians, and they're like, oh, well, if you do that, you should study non-local analysis. And I was like, sure, why not? It seemed like a friendly bunch. I do like friendly people. I go where the universe takes me, and the universe took me to there. But why should you do it? Well, it turns out that it's really good at capturing physical phenomenon in the presence of damage, cracks, fractures. So, like, for example, this is a little cement that has this damage, this crack feature through it, little flower growing through it or a plant, but it's got some damage. And so, for example, here's this, in the background, you see this pipe, and it's corroded, and it's got this huge crack on it, too. So mostly I've been studying materials. Why do it? Predicting material failure, designing more materials, more durable materials, understanding how the materials, will behave under their environmental factors, how the environmental factors will affect the materials for sustainability, for safety, and mores, apparently. Intelligences, though, this is why I applied to come to MOI, and thank you to the NSF, because I wouldn't be here. I work at Hispanic Serving Institution, means I normally have to teach quite a few amounts of courses, but I get to be here and learn from you amazing colleagues. And so I was thinking, understanding human decline, if you can do this for materials, you can probably, most likely, people do this for, and more recently, taking the ideas for non-local analysis on materials, on like biological phenomenon, bone fracture. And so why not understanding human decline more specifically towards the brain? And even here, I'm getting that sense that human brain and artificial intelligence, which came first, the chicken or the egg, I'm not sure, but the human one came first. But the design of the artificial intelligence is at least inspired maybe by human, and some form of human and biological intelligence. Study parallels between like neural and artificial intelligence, giving us insights into learning and memory, and maybe even help when designing like prosthetics for the brain or something like that. So here's the non-local analysis overview. Here's the mathy part. So how do you build a math model that accounts for non-local interactions, and how do you, what about a model that anticipates that what you will be modeling will undergo forces that cause it to behave discontinuously, that it will suddenly break? So I meant to warn you, this is kind of a low budget talk. I like to draw out my slides for you because I feel like it's a little more intimate. So this is what my slides look like. So let's say I started with a grid of points. And I'm so glad this is this kind of talk, because you can choose your visualization, really. In this portion, you can think of whatever your material is, form a grid on it. It could be a grid of points, or you can visualize maybe even a few blocks formed together. Or you can even think of the material points, even ants in the bridges that people have been showing. But for now, let's simplify it and think these represent a 2D material. And I have a focal point in the middle, X. I try to say, choose a visualization. Why I chose these, it's, choose your own, choose what works for you. And you typically choose like a physical law. So to build this mathematical model, it will be a deterministic mathematical model. So I'll choose a law from physics, Newton's second law, force is equal to mass times acceleration. I am going to expect whatever this material, whatever this grid represents, whatever material it represents, is undergoing some forces that's going to cause it to move. So for example, I'm going to start with small movements. some jiggling, like for example, if you all bundled up in the middle of the room and started kind of shimmying against each other. So small movements, right? Huh? Sure. Yeah. Just a typical Thursday afternoon for everyone, right? Let's all do it right now. No, we don't have to do that. So we do that. And so I try to represent this in an image. This one, I'm not happy with this image, but I couldn't think of a better way to draw this. So the idea would be that grid, I erased a couple points, they're still there, just because too many overlapping things. That grid would then, wherever this point was at the original time, when I started observing it, whatever this reference configuration was at that time, it's going to move to a different point at a later time. And that's going to give me this little vector that I could draw and keep track of. That vector I can call a displacement vector. Now I can bring in, and so this is why I tell all my chair, my dean, I can do research with undergraduates because all I need them to know is calculus and a little bit of physics, and maybe even not that, honestly. But as long as they can follow along with this, they're good. I can draw this vector, now I have a displacement, and so now I can figure out velocity and acceleration, so I've taken care of my acceleration term. And this is why I need usually a chemistry or biology student. They can figure out and they understand really well the parameters around mass and something like that. Now I need to describe my force term. So it moved to y. This is my displaced point at a later time. And whatever my reference material was, they tend to call whatever it moved to the deformed state or something like that. And here's my reference origin point so that I can keep track of this in R3. I said this was a 2D thing, and now I just realized I drew this in R3. Sorry about that. So I'm going to switch between visualizations now because I want to talk about forces. So if instead of having this grid separated like this, each of these were little cubes sitting next to each other, like as if these, just little Legos stacked next to each other, jiggling, shimmying next to each other. Because of the symmetry of it, this is where cubes are helpful because of their symmetry. You can keep track of the forces that are acting top, bottom, left, right, front, back, and kind of put a little local coordinate system on each of those faces. Whatever happens in the front, back, I'll put it here. It's going to happen front, back. It's going to capture the symmetries front, back. Blue, right, left, okay? This not important for this talk, but you can get physical information out of doing this. Yeah, so each cube now would have been one of those previous material points. All right, nothing, and this is good for small deformations. These are like forces, shear and strain forces, small though. You'll see why small, because I organize the stresses. It's called a Cauchy stress tensor. And if I consider them to be small deformations, this is a bit heuristic, so sorry for math people in here, but you can imagine that we can obtain a Taylor approximation up to some like surface area terms. The small deformations in the I direction, in the J direction, and in the K direction. And when you pass to the limit of that small deformation, you get a term that looks like this one. It's a divergence of the Cauchy stress tensor, which is all fine. This mathematically works nice, and this what excites mathematicians, and I think mathematical physics types people, right? When the math and the physics work really nicely like that. And so then you have your simple math model. You collected your acceleration term, your mass term, your force term. You can have additional forces, not just the jiggling ones. You can make this embellish it as how you like. But this was used for quite useful for quite some time. But what happens when you can't pass the limit? Like mathematically, you have to be able to pass the limit. That means that whatever you were modeling, whatever forces you were modeling, couldn't really be so that limit had to exist. So to some extent, those forces couldn't be so bad. So what happens? Especially yes.
Could you go please to the last slide? So what is the intuition? What is the problem that is being solved? And what does the Taylor estimation do? Sorry, I'm a little behind.
So we are going to try to capture a model for damage. So without
Even a force that was exerted or no? Like, what is the source of the damage? What kind of damage?
up to you.
Okay.
Yeah, this is really open right
And
now.
then if you go back to the next slide with the equations,
Mm-hmm.
what is the thing that is, no, or the last one, I'm just curious
This
about
one.
this. So what determines a force that is exerting the damage, and how does the Taylor approximation?
Right now, no damage is happening because right now it's just jiggling. Right now it's just a small jiggle. Right now it's kind of, the way I see it in my mind, right now it's kind of like that robot that's jiggling.
I see.
No damage is
So
happening.
this is before the damage.
This is before the
I see,
damage.
okay.
And like your intuition is right. This doesn't make sense for damage. It won't capture damage. It only makes sense for really small deformation. But people would try to use ideas like this and try to embellish somehow to capture damage. Like introduce a boundary that is already damaged and then make it so that it's a small deformation around the boundary or something like that, because you can't really capture the instantaneous damage, right?
Do I understand intuitively correctly that the Taylor approximation looks at small changes and then there is a phase transition at some point that goes into damage?
Maybe. I don't understand what you mean by phase transition.
At some point, it's not just small things. At some point, there is a rift, there is a threshold passes, and then things get actually deformed in a meaningful way, which would be considered damage.
We could be talking about, I'd be curious to know more about that. Can I tell you how I bring in damage? Okay, so this is not the damage. This is a simple model that does not bring in damage. It's not good. And so how do we change it when we have unnice behavior? Meaning, I want to see damage. I want to see this rip, right? Like, what do we do? What do I do instead? So instead of thinking of the jiggling and the people together, instead think, we're still here, but instead we're holding hands or something like that. So now we're not jiggling against one another, we're holding hands, and it's almost like we're exerting forces on each other that way. So it's still the same grid, and now I've still embodied the material in the reference material domain and called it omega. But I've highlighted some neighbors of the point X in the non-local community. You call this horizon or zone of interaction, right? Whatever you want to call it. It's a ball of radius delta. It's a zone of interaction. It's the neighbors that are going to have relevant forces on you that you're going to consider towards what happens next, towards the forces that are acting on the point X. And the nice thing about the non-local modeling, because you're capturing these volumetric forces within this delta horizon, it doesn't need to only come from your nearest neighbor. It could come from neighbors further away, and this is where you capture those longer range force interactions. So it doesn't only have to be your local neighbors. You can widen your horizon a little bit and capture forces coming from further away. And so, so again, why non-local, and then how do we formalize this? So going back to the cubes, sorry, I'm moving back and forth between cubes and dots. Analysts like cubes. If you had cubes, like say you had two open cubes, but they shared this yellow surface. So if you closed them and intersected them, it would be that yellow surface, and it would be not empty. It would be that yellow surface. There's some way to define some kind of classical interaction through flux between those two surfaces, but they have to touch just so. Now, if those cubes were coming apart or were fully apart, you would lose that interaction flux. That flux definition would not be that flux, the classical definition of flux would not capture any interaction between those disjoint sets anymore. So it turns out that, at least in this paper, a whole framework of definitions came out where you can define a flux between two disjoint sets in a meaningful way. You capture the action-reaction principle, so you can really do a lot of mathematical physics types modeling with this idea that I'll just consider forces, in a zone of interaction. And so, I won't display the whole framework, but this is the basis. This was all inspired by a paper written in the year 2000 by Stuart Silling. I don't think I put a reference to this paper in this talk, but I cannot give this talk without mentioning it. But I did want to give a little bit of intuition for how one as a mathematician would cook up one of these non-local operators. So this is a bit intuitive, and it's motivated by some of the dream talks. So begin with a dream and end in reality. So let's say we expanded the function that your dream function, u, going from r to r. I'm not saying that this function is expressing any damage or anything. It's your dream function in a Taylor series, and it's centered at x, and it's evaluated at x plus y. And as you're doing your dream Taylor series, you kind of focus on this second order derivative term, and you stop right there and you say, well, I realize I could look ahead into the future. I can isolate that second order term by integrating with respect to y on a convenient domain. These are scalar value functions, but it's on a convenient domain because now I have this odd function, so it didn't really matter what u prime of x was. I can really isolate u double prime x. And I just need to have some integral properties of the function u. But it doesn't stop. Did it change? Yeah. So 0, because this is an odd integrand, and some constant that depends on delta. But it doesn't stop there. You can play around with this a little more. You can say I can also select an integrable and radially symmetric function mu and multiply it on the left and right-hand side, so long as I'm not cheating. I am using my license to math right now. And when that happens, I can do so in a way that this odd is preserved. This is odd. I'm still focused on that second order derivative term. And so then you come out with something that up to, something order delta squared, is behaving like a second order derivative on u. And if you choose, the reference to this paper is here, but if you choose, certain type kernels, you can choose that in some sense this converges to, in some weak sense, this converges to the Laplacian operator as well. So this is how you would come out with a non-local operator. This is one way to define a non-local Laplacian type operator. It's not the only way. And so then people study those how do you choose those kernels? There's prototype kernels. There's been a lot, this kernel's shown up in the tutorials in this workshop too. And this was what you will see and what I was told too when I entered the non-local world, that this is the prototype kernel, the prototype kernel. And it's nice. It's got some features. If you have your function, I'm just defining the non-local Laplacian. When it's defined, it's typically defined in this fashion. Instead of having just mu, for example, over here, it'll be written so that it's written as alpha squared to be a little more suggestive of its second order derivative nature. And the prototype fractional Laplacian kernel is chosen so that it takes this form or some variation of this form. And it has these kinds of properties that when this is n, the order of your space, and this s parameter between 0 and 1, the closer it is to 1, the closer you are to the classical Laplacian. And the closer that s parameter is to 0, the stronger your model will have long-range interactions. So I think those, or at least to my knowledge, that I can share, these are some of the reasons why these have been the prototype kernels, their relationship to the Laplacian, and the ability to capture these long-range interactions. And I didn't want to include so many definitions. There's so many definitions in this, but I wanted to include the non-local gradient. The divergence and gradient have these sort of adjoint relationship to one another. There's more than one way to define a non-local gradient, but there are these non-local two-point gradient. Just wanted to share those definitions, and that there are also non-local curl, interaction operators, point Carré inequalities. So there's a lot of directions you can go with this. It's really overwhelming, I think, when you first come in. But I've been wanting to study a little more the non-local gradient because the gradient, the classical gradient, right, appears in many phenomenon, like even like a lot of analysis inequalities of uncertainty and things like that. And I don't know. I don't think they've been studied from a non-local perspective. And so I think this was a little bit of my contribution to the non-local community, the non-local Helmholtz-Hodge decomposition. So the question was, if you're given a two-point vector field, so it's just a vector field whose inputs, you have 2 points as inputs, x and y, can it be decomposed non-locally? So can you decompose it into something that's like a non-local incompressible and a non-local irrotational term? This has many applications in like fluid dynamics and magnetism. And will there be a third term in the decomposition like the classical Helmholtz-Hodge decomposition? And the short answer was yes, there is a decomposition and there is a third term. And this was interesting because in n is equal to 3, typically, except for some situations that depend on the boundary, this decomposition comes down to just the 2 terms like this. But non-locally, you necessarily have a third term because the way that the operators are defined in the non-local realm, the kernels of the curl and the divergence are not empty like they are in the classical case. And so there's a reference for this paper. I just had to share this picture because my beautiful collaborators. And I also took this as a point to mentally pause and share a comic with the audience for comic relief and just mental pause, and to see if there were any questions. Mm-hmm. Sure.
Yeah, so it looks like you're developing a long-range Laplace operator so you can model like fracture on materials. I was thinking like fracture is more of a local aspect to it. Why do you need like a long-range operator to describe it? Or maybe my assumption that it's local is maybe incorrect.
Well, I think the biggest area, and I didn't go into this work, but the biggest area where, at least when there was cracking that had this specific kind of like branching. I'd have to send you references of specific people and papers, but in this kind of very specific type of cracks, the classical methods fail at capturing these specific kinds of loads where the crack is going to be like this. Certain cement cracks, glass cracks, certain ceramic failures are not captured accurately using the classical methods, but in the non-local methods, they're captured really well. The one that I'm going to talk about is electrochemistry, and this one I know for sure why. I can answer you with more certainty why it's non-local. Yeah.
You wrote an integral operator.
Yes.
And are you sure that it's +2 should be -2 and -2? Because for Laplacian you have 1 over r in 3D. So if n is 3, you wrote something which is 5 plus something, so it should be -.
It probably should be -2.
It's okay.
Yeah. I don't know.
So then non-local Laplacian is good for these long-range things. Is it like there is a point that you crack a window, there is cracks in all directions going, so it's a little bit almost like traveling on a graph of points, and it has to do with the notion of reachability to some extent, where the inverse of the Laplacian is sometimes used for I wonder whether that is the kind of one of the reasons why these long-range things matter, just to go back to what Eder was asking, basically.
I mean, when I look at simulations done of glass cracking specifically, where the non-local models agree with, it depends on the loading conditions and the experiment itself, it sounds like what you just described. So I'm tempted to say yes, because what is interesting to the researcher is specific, like, I guess glass doesn't crack in the way that we see it in animations, right? It's like what you said, right? They have, yeah, you have to see it in real life. You have the place where, and it branches like this, or it might branch like this and one up or something like that. And those are the little ripples that you want to capture. And the non-local operators are pretty good at this, but you do have to fine tune the parameters.
Yeah, because it's not diffusion in all directions, it's
No.
particular ones. And I wonder whether this particularly captures that.
It does.
Nice.
And I don't do those, but it does. And for example, the last conference I was at that was dedicated to non-local was just when this the bridge had collapsed, and so it was very timely because the type of cement fracture was very non-local in its behavior.
Interesting.
Yeah.
Is it similar to the theory of dislocations in crystals? Because there are also point defects, there are strain fields, and dislocations that are of different type and they move with something really different.
That's one that I cannot answer with any kind of certainty. Yeah, because I just don't know about crystals. But that would be interesting. Mm-hmm. Yeah. And a student shared this comic with me, and it's a good one. Okay, so now the peridynamics and the fracture of material. So now to the peridynamic equation of motion. This is just where we replace, now to answer your question, this is just where we replace those, we don't consider small deformations, we consider volumetric forces acting on the bonds. So instead of cubes jiggling, we think what are the forces acting on our hands moving, on our hands holding, that would cause them to become damaged. So here's our reference domain, the point X, some other point in the zone of interaction, the bond Xi, the displacement vector U, where the point Y, where it gets displaced to, U prime, I guess I could say, and Xi plus eta, and eta is the vector which I would call the displacement vector, the amount by which Xi was displaced. And so the idea would be to try to describe, what are the forces acting on Xi. And there's a little more. There's more than one way to do this. This is maybe the most straightforward one to describe, and the one that's most related to what I'm going to show next. It's called the bond-based equation of motion. So you take your force. I should say this before I move on, though, because the way I wrote it there, if you do, so even though the next page thing doesn't work, the pointer should still work? Okay, good. If you do U minus UX prime, you'll get this, you do a quick little computation, you'll get just the eta part. And you do Xi prime minus Xi, you'll get X prime minus X, you'll get Xi. So this force really just depends, it's some force that you'll write that depends on Xi and eta. That's what I'm going to write on the next page. And the standard force that you would write down at first is the force in the direction of the displaced vector, maybe normalized, and depending on some constant terms. This C is micromodulus. This S it's called bond strain, but you can think of this as the relative stretch of your bond. And this mu is a bond damage factor. So you're just going to collect if your bond strain has reached a critical stretch or not. And you can be as creative as you want. For example, you can add something like, maybe this isn't enough. You want to say, I want to add, if the bond breaks, some probability that the bond will break or something like that. And then you collect a damage index. And then you can say, I'm going to look at my grid, and I'm just going to look at my bonds. And if they're broken, I can just collect a damage factor or something like that. And that's how they've been good at capturing those cracks in glass, cement, things like this. These kinds of branching. This page just has some references for the bond-based modeling in the corrosion case specifically. And I'll tell you a little bit about corrosion. Of course, you know that corrosion is a problem. It's very expensive. It's one of the United States spends billions of dollars on corroding metals, especially in the military. And so what happens and why this one is a non-local problem, let's say you have a metal. So now you have little material points that are metal, let's say iron. Are there chemistry people in here? In case I need a backup. So, okay. So, but I think we know enough about chemistry. And this is some electrolyte, and there's water molecules in the electrolyte. But my metal, let's say my iron atoms, the outer electron ring, I think only has 2 electrons, which is, I think, not ideal for atoms. They want to have a full electron ring. They want to have 8. The water molecule only has 6. They're almost full, so they're attracting those 2. So those 2 are going to be attracted to this one. And when they do, they'll leave a little bit of rust deposit. And this is where the non-locality is going to come from. They'll attract those 2, and so without those 2, it'll release metal ion into the electrolytic solution. It'll release the metal ion, it'll diffuse through electrolyte, and it's going to influence corrosion rates away from the site where it was released. So this is where the non-locality is introduced, and it's going to also result in a net electric charge. And so this is what's going to start once this little chain reaction starts, it's going to cause a little bit slightly diffuse, but also a non-local phenomenon. Okay, one of my students, I drew this little cartoon for our group. So in this electric charge will give rise to electrochemical cells and a formation of electric potential at the metal surface. So where the ions escape from will form what's called an anodic region. The electrons will be escaping. They'll be attracted to cathodic regions. It's not drawn to scale. These should be perpendicular. And so I had some physics students that got really interested in this. But the reason why I said go for it is because there was this paper that said, well, if we, in this paper, they were plotting the distribution of current densities in an electrolyte at different times, and they were observing discontinuities in the current density. So I said, if we're going to study, electric potential and current density, and there's a discontinuity in the current density, then we can study it and derive some kind of non-local model for it. Go for it. And students were very happy. They started building stuff and did, trying to get mathematical models for it. And I thought, that's great. And in the meantime, there were these good papers that supported that it's a good idea to study this, and gave some reasonings for why a bond would break, for example. This one maybe is not for why a bond would break. I should have labeled it something different. But it said, let's say, in this paper, they said, for example, if you have the concentration of iron particles, if it reaches a critical value, you're going to get damage. And so they just changed the framework from, supported by the actual physical phenomenon, they took the rate of change of the concentration, and they took a concentration gradient that is non-local. And here they did use the classical Laplacian, but in its non-local form. They did add this bond break term. I think they called it bond breaking probability, but it's like a rate at which the bond breaks according to its concentration. So they updated their damage factor. And so they got fun with it, They had some conditions under which this bond breaks, and they used a bond break model. They introduced the effects of electrochemistry. In theory, they said you have the effects of electrochemistry, but they didn't implement it in their code. They shared some code online that I'm going to share with you as well. And they have some pretty good results. So this kind of discontinuity they captured with their non-local model. So some takeaways from that. When modeling corrosion, account for the dissolution or the diffusion of ions in your material damage happening at the same time. The current density is proportional to the corrosion penetration rate. So this thickness loss per unit of time, and you can implement this model and get quick results using something called PeriFast or PyNucleus, and they're free to use online. They're great. PeriFast was designed by a group led by Florin Babaru at University of Nebraska, Lincoln. Just really great tools. And this is the dolphin and PeriFast. If you go to PeriFast on GitHub, you'll see the logo for University of Nebraska. It's a big N, a big red N. And it's really cool. You download it, it runs without any issues. And so I was showing it to some computer science faculty, and they were like, why are you showing us someone else's logo? And I said, it was easy to use. I mean, they said, you should make dolphins corrode. It's like, oh, I've done weirder stuff, so sure. And so I have a YouTube video, but I think it's better. I think it's better to just show you. I don't. The only thing I haven't figured out in MATLAB, so sorry, folks, is how to save this as an MP4. So I'm going to just show it to you. It runs really fast. I've already, compiled everything that I needed. So there's a little dolphin, and there's a little pit that forms. And the reason, and there's a little, it's a mom and a baby dolphin. I'll show you one more time. And the reason why it looks still cartoonish, you see the pit forms and it's corroding away. It's super fast. Is this IPAM? Yeah. Here's the YouTube video of that. Is because in the implementation of PeriFast, they did hold the current density constant. And I'll show you in a little bit that in these situations, it's not really constant. So now when you have instances where you have fractional Laplacian or something like that, and you want to do some kind of finite element method analysis on it, I'm going to show you, I'm actually not going to show you the mathematics. Happy to talk about it later, because I didn't realize how time flies when you're up here. I'll just show you that it works very similar. And actually, you would have caught another typo. This isn't in the, these test functions really are in the Hilbert space type structure, but this is a bilinear form, not in this classical Hilbert spaces. It's we use an H, but I should have made it curly or something like that. It's it uses that non-local gradient, and that's why I defined it. And it takes a little massaging to see it as this bilinear form, but it's actually a really fun computation. And so then you get some kind of something that some linear system. It looks like finite element methods. It uses the same hat functions, but then you can do some simple simulations. I don't know what that 5 is down there. I don't know where that came from, but you can implement it and you can see some. I'm not sure. I'm not fully sure why we see the spikes. Like S is the fractional power. Remember, S closer to 0 means more nonlinear interactions. S closer to 1 gets you something closer to the classical Laplacian. And because these are N is, this is the only harmonic functions you should see with these like boundary conditions should be aligned. And that's what you see. That's what I expected to see. Starting to get closer to like a line. In 2D, things get a little more funny, but there was a nice paper. I hope I referenced, maybe I didn't reference the paper. I did at the end, I hope. A very nice paper you can follow. They don't have it on GitHub, but you can follow along and solve for these potentials. And the reason why I'm interested in solving for these potentials is because holding the current, it's a relationship to the current density, holding current density constant isn't enough to really capture a realistic simulation of damage due to corrosion. And then you can have fun with them and make it look weird and stuff like that. And there's that relationship between potential and current density. Even non-locally, this is true. And then you can just do a quick little transformation and you'll see your current density maps. They look funny. That's what they look like. Students had a great time building machine. I didn't include a picture of the machine. This is a schematic of their bot. They call it the Shred bot. They also went ahead and studied some microbiologically induced corrosion, which is a thing. They just took a bunch of different bacterias, grew biofilms, put them on steel chips, and see how much more corroded the chips were or weren't. I forgot to say, this SRET bot, you can ask me about it, but this SRET bot speeds up corrosion so that we can study corrosion and validate and stuff like that. I wanted to get a little bit to the new horizons. I'm gonna have to put this one in the Slack channel. But basically, this is another mental note. Have you seen this comic? You've seen it, yeah. Hopefully it includes everyone. On the first one, it kind of bothered me at first. Like, it's the range from sociology to mathematician by purity or theoreticalness or something like that. But I related to it because I related to it here, fields arranged by complexity, where sociology really is the most complex of our fields. And me as a mathematician thought, wow, it really is easiest to deal with all these quantities without thinking of units at all. You really see that. I haven't really mentioned anything about units. And I love the engineers over here telling us, hey, you guys should really find a job instead of debating field superiority. Anyways, okay, so this non-local operators appear everywhere, non-local kernel networks. But where I really want to study them is in modeling neurodegenerative diseases. There is some expectation for non-local strain energy. And in this paper, which was not published not too long ago, they give a reason to avoid non-local operators specifically, but I don't think they were complete in their analysis. They say that they avoid it because they want to avoid spurious interactions between neighboring but disconnected regions. I think there's ways to ensure that doesn't happen if you're careful. So that's something just want to put out there. And also non-local models in the analysis of brain neurodegenerative protein dynamics with application to Alzheimer's disease. This was 2022, if I'm not mistaken. Now, these two authors just this year posted on arXiv some applications of non-local models in all sorts of biological and life applications. But in their model, I felt it was really dynamical systems model with some non-local operators thrown in there without, at least I didn't see the full, I didn't see like a really bond or graph-like model that spoke to me in terms that I think are more understandable coming from this audience. Like all the talks that we've heard here. So I think there's room and there's growing interest for non-local models in the space. And so there's the arXiv reference. And so I really want to just thank my recent collaborators. This is probably where I'm going to stop anyways. These are my recent collaborators. Check out Cracking Math podcast. I really want to shout out to Trent Ruiz, who's got the purple hair on the top left. Just took a real big role in Cracking Math and writing that NASA grant. FathomWorks is a local Navy lab, and that's exactly why we got into corrosion specifically. I didn't think it up one day. They kind of asked, if you do damage, like, can you do something about metals corroding simulations with that? And the answer was yes. And here are the references.